Hi, this is Pat Kaplo, and I'm solving problem number 18 on page 131 in the textbook. The problem reads, in a rotor ride at a carnival, people are rotated in a cylindrically walled room. The room radius is 4.6 meters, and the rotational frequency is 0.50 revolutions per second. When the floor drops out, what is the minimum coefficient of static friction so that the people will not slip down? So I've made a sketch here of a person inside this cylindrical drum, and they are obviously spinning around in a circle. At some point here, the floor drops out from underneath them, and the question is, what's the minimum coefficient of static friction so they don't slide down in this direction here? So as with all dynamics problems in circular motion, we'll start with a free body diagram, and we need to really understand the forces acting on the person before we can write some equations and move forward. So of course, when the floor drops out, we know that we have a weight vector in the downward direction. And in order for them to move in a circle, they have to have some sort of a center-seeking force here. And that's provided by the wall. If this wall were not present, then the person's not going to move in a circle. They'd fly off on some straight line tangent to the circle at the point that we remove the wall. So the normal force on the wall is really an important idea here. Without the wall pushing them inward towards the center of the circle, they would not be moving in a circular motion. And once the floor moves out from underneath them, it's going to be a frictional force. So what's stopping them from sliding down the wall? It's a friction with their bodies in the wall. Notice that the frictional force is going to be affected by this very large normal force. So you're going to have this high frictional force supplied by N. That's what our free body diagram ends up looking like. And so now we're ready to go ahead and move on with our equations. We can say, importantly, in the horizontal plane, we can say that the normal force is equal to the centripetal force. We can see that here because that's the only force acting in the horizontal plane. So now I can substitute mv squared over r. The normal force is equal to mv squared over r. When I take a look at things in the vertical plane, there's a little bit more going on. I can say that the frictional force is positive, so the frictional force F minus the weight is equal to 0. We can say that it's equal to 0 because we don't expect the person to be accelerating in that plane, upwards or downwards. So the sum of the forces will be 0. They'll remain at rest. I can substitute mu static times the normal force in for friction and subtract from that mg is equal to 0. Now, of course, as in many of these problems, we see there's an opportunity to substitute that expression for normal force. I'm going to bring the mg term to the other side in the same step that I substitute. So I'm going to get mu static times mv squared over r is equal to mg. So I've performed both the substitution and I've added mg to both sides. I see now that the mass cancels out of the term on either side. And since I'm trying to solve for this variable, mu s, that's the term that I'm trying to isolate. So I'll leave it alone on the left-hand side and multiply both sides by r. I get mu s times v squared is equal to g times r. And my final step to isolate the coefficient of static friction is divide both sides by v squared. I get mu s is equal to gr divided by v squared. And I'm ready to plug and chug. 9.8 meters per second squared is my gravitational acceleration. 4.6 meters is the radius of the room. And aha! What is the velocity? That's really one of the critical steps in solving this problem. So probably could have started with this, writing down what we know. We know that the radius is equal to 4.6 meters. And they give you this other piece of information, this so-called rotational frequency of 0.5 revolutions per second. We've talked about this in class. This should set off some sort of a flag for you anytime you see RPM or RPS. They're communicating to you the speed of the object. In this particular form, it's rotational speed, but we can get something more usable from that by a little bit of dimensional analysis here. So I'm going to get 0.5 revolutions in 1 second. And I know that 1 revolution can be converted to a linear distance by the equation 2 pi r, where r is equal to 4.6 meters. The revolutions will cancel out, and I'll be left with meters over seconds, which is really what I want. When I do that, when I run that through the calculator, I'm going to get something on the order of about 14.5. I got 14.45 meters per second is equal to the velocity. Now, in that form, I'm ready to plug it in. And so I can put that here in the denominator, 14.45 meters per second. Of course, don't forget to square that. Running that through my calculator, I can find that the minimum coefficient of static friction required to make this ride work is about 0.216. Of course, the coefficient of friction is unitless. I should truncate this to 2 significant figures, so I'll call that mu static is equal to 0.22 and call it a day.